In this video, we will use the limit definition to rapidly expand our inventory of derivatives. The process of taking derivatives of functions is called differentiation. We will discuss the additive property of the derivative and how that applies in particular to provide simple rules for differentiating polynomials. I will explain why the natural exponential function replicates itself under differentiation, and also sketch a proof that the derivative of the sine function is the cosine function. In an earlier video, we gave a definition of the derivative in terms of limits. Let y equal f of x be the rule for a function f. Remember, we define the derivative of f at x, denoted by f dash x, to be the limit as h tends to 0 of f of x plus h minus f of x divided by h. You can also remember this limit formula captures precisely the value of the slope of the tangent line to the curve at the point of interest. By now, you're probably starting to picture this phenomenon in your mind's eye and the idea of the limiting slope of secants. We have already applied this formula to discover that if f of x is x squared, then the derivative is 2x. And if f of x is x cubed, then the derivative is 3x squared. More generally, if fx is x to the n, then the derivative is nx to the n minus 1. The simplest functions that differentiate quickly are the linear functions with rules of the form f of x equals ax plus b, where a and b are constants. The graphs are just straight lines. If you reflect for a moment, the only reasonable way for a given straight line to be approximated by a tangent line is to take the line itself. And the approximation is so good, they match perfectly. In other words, a straight line coincides with this tangent line at every point and has slope a, so that the derivative must be just a. You can check for yourself that this follows quickly from the limit definition. In particular, if a is equal 0, so that fx equals b, which is a constant function, then the derivative is 0. If f of x equals x, then the derivative is 1. The derivatives are additive, by which we mean that if f of x is the sum of two rules, u of x and v of x, then the derivative of f is the sum of the derivatives of u and v. Constants come out the front in the sense that if f of x is k times g of x, where k is a constant, then the derivative of f is just k times the derivative of g. This follows easily from the corresponding properties of limits, and details are in the notes. It's now straightforward to differentiate any polynomial. You can differentiate any power of x. You see, you can differentiate any power of x, you see, multiply through by any constant you see, and add everything up. Let's take an example. Let's take this polynomial that is of degree 4. And let's differentiate each term and see what we get. So when we differentiate x to the 4, we get 4x cubed. When we differentiate x cubed, well, we get 3x squared. Constants come to the front, we multiply by the 2 in front. Then we differentiate x squared, we get 2x. That is multiplied by the constant in front, 5. Then we differentiate x, we get 1 times the minus 3 in front. And then finally, when we differentiate 8, we get 0. And we simplify. Notice that differentiating a polynomial decreases its degree by 1. So you can always make a polynomial disappear if we differentiate it often enough. To illustrate, let's use an example. Suppose f of x is this quadratic. If we differentiate this quadratic, this is what we get. We now have a linear function. If we differentiate again, notice we have a constant. We call this the second derivative. If we differentiate once more, what do we get? We get 0. So the third derivative makes the polynomial disappear. If you take a polynomial of degree n and differentiate it n plus 1 times, then it disappears. Next, we look at a function that turns out to be indestructible with respect to differentiation. Consider the function y equals e to the x. Recall from an earlier video that the tangent line to its curve at the y-intercept has slope, 1. The base is Euler's number E and is chosen deliberately so that this property holds. We want to transform this fact into a very specific limit. Let's have a look at the curve for x close to 0. If we input x equals h, some small positive real number, and move up to the curve, then we have the value e to the h on the y-axis. Now, let's draw a secant that joins the curve's y-intercept to this point at the curve. The slope of the secant is the vertical rise e to the h minus 1 over the horizontal run h. As h tends to 0, this slope tends to the slope of the tangent line, which is 1. Thus, the limit as h tends to 0 of e to the h minus 1 over h is just 1. This limit is very special, and in fact, the foundation for the central role Euler's number E plays in mathematics. Now, let's prove the following. That is, we want to prove that f of x equal to e to the x. When we differentiate it, it remains unchanged. It remains e to the x. Here is the proof. First, write f dash x using the limit notation. The numerator inside the limit then becomes e to the x plus h minus e to the x all over h. But e to the x plus h can be rewritten as e to the x times e to the h by applying an exponential law. Then this new numerator factorizes as e to the x outside times e to the h minus 1. But e to the h doesn't involve h at all. So it's like a constant that can come out the front of the limit. So we'll get e to the x times the limit as h tends to 0 of e to the h minus 1 over h. But this is the special limit we identified before, which evaluates to 1. So the whole expression becomes e to the x times 1, which is just e to the x. And the claim is proved. This is an amazing fact. This function reproduces itself upon differentiation, no matter how many times you differentiate it. The circular functions y equals sine x and y equals cosine x form a pair of indestructible functions from the point of view of differentiation in an interesting roundabout way, as you will soon see. We claim that the derivative of sine x is cos x. I'm going to sketch a proof, but the proof will involve an advanced mathematical argument. If you don't follow all the detail, don't worry. I'll first try to convince you visually that the claim seems plausible. Here is a graph of y equals sine x. And directly beneath it, we're going to draw the graph of y equals cos x. Here are points on the sine curve having slope equal to 0. Notice the cos x takes the value 0 for exactly the same inputs. Let's also focus on points where the tangent lines of y equals sine x have slope positive 1. Notice that cos x takes the value plus 1 for exactly the same point. Finally, focus on points where the tangent lines y equals sine x have negative slope. And by that we mean negative 1. And notice that cos x takes the value negative 1 for exactly the same inputs. So our claim is looking plausible based on these samples of points. Now, we're going to sketch a proof of this claim. There are a lot more details in the notes. As preparation for the proof, let's first look more carefully at the tangent to the sine curve at the origin and ask for its slope, which looks like it should be 1. Take a point on the curve and form the secant that joins the origin to this point. The horizontal run is some number h, while the vertical rise becomes sine of h. So the slope of this secant is sine h over h. So the slope of the tangent line is just the limit of this expression as h tends to 0. But we were introduced to this limit in an earlier video, and we know that the answer is 1. This confirms that the slope of the tangent to the sine curve at the origin is 1. Let's look at the tangent to the cosine curve at x equals 0. Because the cosine curve turns around at that point, the tangent is horizontal. So the slope is 0. Let's interpret this as a limit. Join the point at the apex on the y-axis at y equals 1 to some other point of the curve, forming a secant. The new point has coordinates h on the x-axis and cos h on the y-axis. The secant is sloping downwards. In moving along this secant, the horizontal run is h, and the vertical rise is actually a decline of 1 minus cos h units. So cos h minus 1 is negative. And if we divide it by h, in moving along this secant, the horizontal run is h, and the vertical rise is actually a decline of 1 minus cos h. So cos h minus 1 is negative. And if we divide it by h, we get the negative slope of the secant. We have 0 being the slope of the tangent line. Which is also the limit as h goes to 0 of the slopes of the secant. We have that the limit as h goes to 0 of cos h minus 1 of the over h is 0. Thus, we have two particular limit formulae. one involving sine and the other involving cosine. There is also an identity from advanced trigonometry that we want to use. And here it is. It's called the compound angle identity. Let us now sketch a proof that the derivative of sine x is cos x. Let's start off with a definition of the derivative. And this becomes the limit as h tends to 0 of sine x plus h minus sine x all over h. At this point, we rewrite the numerator using the advanced trigonometric identity we mentioned a moment ago, with angles x and h taking the place of alpha and beta. We now strategically reorganize the components of the numerator. In the numerator of the first limit, we take out a common factor of sine x. And in the second limit, we have the factor cos x, which behaves like a constant, so it can come out the front. But now, in the first piece, sine x is behaving like a constant, so it can come out the front. The first piece is just sine x times 0. And the whole thing simplifies to cos x, which finally proves our claim. What's the derivative of cos x? The answer turns out to be negative sine x. You can convince yourself by looking at graphs, thinking about tangents to the cosine curve, and checking against corresponding points on the negative sine curve. The rigorous derivation using the limit definition appears in the notes. You're probably curious now about the derivative of tan x. You're not likely to guess the answer. It is, in fact, the reciprocal of the square of cos x. You'll have to wait for a future video to see why. We showed before that the derivative of e to the x is e to the x. We've just shown that the derivative of sine x is cos x, and mention that the derivative of cos x is minus sine x. This means that the circular functions are indestructible in the following sense. If f of x is sine x and the derivative is cos x, so each derivative the second derivative is sine x. The third derivative is cos x. Sorry, negative cos x. The fourth derivative is sine x again. And we're back to where we started. So differentiating over and over just reproduces the same cycle of functions over and over again. Today, we've really come a long way using the limit definition to rapidly expand our inventory of derivatives. We discussed and illustrated simple rules for differentiating polynomials and noted that by differentiating often enough, we can make a polynomial disappear in the sense of going to zero. We explained why the natural exponential function reproduces a perfect copy of itself under differentiation. So in a certain sense, the function is indestructible. We also sketched a proof that the derivative of the sine function is the cosine function, and mentioned that the derivative of cosine is negative sine, leading to an indestructible sequence of functions: sine, cosine, negative sine, and negative cosine, that reproduces itself forever under differentiation. Please read the notes, and when you're ready, please attempt the exercises. Thank you very much for watching, and I look forward to seeing you again soon.